I'm very happy to introduce Phillipp, who's been doing work on interesting cryptographic protocols sort of at the cutting edge at Google for a number of years now, and is going to tell us about what he's been working on secure aggregation.
Yeah, thanks. We had a lot of talks already about secure aggregation, so I hope that the basics don't bore anyone, but I try to skip over them quickly. This is joint work with a lot of people at Google, Kazura, James, Benedict, Adria, Hossein, Bayu, Mariana, and Pierre. Not everybody at Google, but like Google plus collaborators. So the setting is, well, what do we actually want to achieve? So we have a lot of data in a lot of devices, like billions of them around the world. And ideally, we would like to learn about the user populations, right? We want to have large-scale statistics, but we don't necessarily need to know about individual users. So the goal is to learn something like histograms, for example, right? So the distributions of things that happen on the device. So in mathematical representations, this could be vectors. Every user has an input vector, x I1 to ik, and we want to learn the sum of all these vectors at the central server. And we have some kind of adversary model that is pretty strong, I would say. So we don't trust the central server. And in particular, we think the central server could be malicious, so can misbehave arbitrarily from the protocol. And in addition to that, of course, we don't know anything about the clients. The clients can be phones that run anywhere in the world, could be browsers even, could be like very untrusted devices. So we don't really want to make a lot of assumptions about the behavior of these clients. And in addition to that, since they are like wireless devices, their connection is usually not that great. So they can drop out at any point, they can never come back, they can come back after weeks, like we don't know. So that also means we have to somehow restrict the functionality of things that we can compute. So we have to maybe limit ourselves to computing the sum of the vectors of the clients that don't drop out, so the surviving clients, which is a limitation in many ways, but we'll see more about that. Okay, in terms of threat model, there are also like additional assumptions we need to make in order for this to work. So there's been a lot of talk about single server solutions versus two server solutions. In addition to these non-collusion assumptions, for example, we need to make for two server solutions. Additionally, of course, we also have cryptographic assumptions. So something like learning with errors or DDH or what have you not. One argument that I actually want to make throughout this talk is that there's not a huge difference between these two models. So single server solutions and two server solutions, fundamentally, they use different techniques sometimes. So PRIO looks very different from what the original SecAgg looked like. But in terms of assumption, you can think that like if you don't have this model where everybody talks to everyone in the single server, and we saw in a previous talk today that this usually doesn't scale, and that's why we don't do it anymore. You're forced to go to some committee-based solution. So you are forced to have some kind of committee that aids the single server in the computation. And once you have that, you already see the pictures look very similar. So a committee-based solution and a two-server solution fundamentally is not that much different. And this is even more so if we try to keep the work on the committee low. So we want, again, the committee to instantiate it with, for example, mobile phones. So we cannot send arbitrary data to those mobile phones. We cannot have them perform arbitrary computations. So we want them to be very lightweight and very easy to implement, easy to deploy. So that again brings us in a similar space that we saw earlier in Ryan's talk, where the second server essentially could also be thought of as a phone or something that needs to be very cheap. There are a lot of other works that are in this single server plus committee setting. So we heard about Flamingo today. OPA is another one, Learner, and I'm sure there are others that I didn't mention here. Okay, so Willow runs in exactly that setting. We have a single server that gets data from a lot of clients. And we have a decryptor committee that is used to aid the computation. One important property is that the clients only speak once. So as we heard, we don't want to have expensive computations between the clients. This, just the clients will drop out throughout the protocol, so it will, as rounds progress of the protocol, that becomes more and more fragile. So having clients send a single message just solves this problem immediately. So that's why one-shot clients are very important. And yeah, as I said, like everything I talk about here It is instantiated for a committee, and the implementation assumes we have a committee, but might as well be instantiated in a single server. And in particular, I think if you implement the latest version that I will talk about, WillowFold, and put that in a second server, you could have a very lightweight, independent of the number of clients, independent of the model size, and so on. Okay, so let's dive into how do we implement secure aggregation with one-shot clients, with this committee-based decryption, like what can we do? And a very simple baseline that I call the HE additive homomorphic encryption baseline has been around for years. So there was some paper in 2010 that already suggested something like that. And the idea is we encrypt our inputs, the input vector, under an additively homomorphic encryption scheme. That could be something as PAYE or LWE-based things. And then the server just homomorphically adds up your encryptions. And in the end, we have the decryptor that I'm now going to keep as an abstract box, decrypt this encrypted sum. So that should already work, right? We have a public key on the decryptor. The clients know the public key. It all works out in the end. Of course, it has a lot of caveats for why it's not so simple. But one of the biggest ones, and that's one of the main contributions of Willow, is that we don't want this length proportional to the inputs on the decryptor. Because again, if we think of use cases like federated learning or even like statistics over large spaces or large domains, that means that these could be megabytes that we have to ship down to devices, then they have to do some decryption, then we ship it back up. So that's already pretty expensive, and we want to avoid that. So one way we do that is by using a key and additively key homomorphic and additively ciphertext homomorphic encryption scheme as an additional wrapper around. The idea now is that under the HE scheme, we don't encrypt the vector directly anymore, but instead we encrypt a randomly sampled fresh secret key for this KHE scheme. And then in the end, at the decryption step, we don't need to decrypt, does this work? Yeah. We don't need to decrypt the entire vector anymore, but only a short key. So if we implement these with RLWE-based encryption, then this will be a vector of like length 4,000, so it's not terribly long. And again, we can encrypt like X vectors here that have length in the millions or billions. So this is already the first step, and of course the challenge is how exactly do we implement this KHE scheme, right? So how do we choose parameters? How do we make sure that it's secure in the end? But the high-level picture is very similar. And it's similar to how you do hybrid encryption when you do public key encryption, right? So you have a symmetric encryption scheme for the large payload, and then you have an asymmetric encryption scheme for the public key part. Like one challenge is that this decryptor needs to be implemented as a threshold scheme. So what we do here is something that's kind of similar to original SACAG. We have a recovery phase where basically decryptors, in the beginning, they secret share their state among all the other decryptors using something like Shamir secret sharing. And then if at the decryption phase some of them drop out, we can recover their state using the remaining decryptors. But one thing that we haven't solved here yet, and that's going to be like the focus of the next slide, is that like secure aggregation has a fundamental problem when it comes to malicious clients. So in this setting already, since we're working with homomorphic encryption, like we can in particular have a client not encrypt their genuine input, but somehow collude with the server in a way to generate a ciphertext that is, for example, the sum of multiple other client ciphertext. And as I try to point out here again, like we have multiple failures of trust assumptions that could come together. So once we have a malicious server, we have a malicious client, and in addition to that, we have dropouts of clients. So we could in particular have a server that drops out all of the clients and only decrypts a single target client, right? So how do we get around that? One mitigation for that is having a PKI client. And again, in the morning we saw a talk that did that. So where you basically assume you have identities for clients and you check them at the decryption step. Another option is to use differential privacy. So to basically add noise to the output in a way that even if the server drops out everybody except a single client, then the output is still noisy in a way that doesn't reveal private information. But what I originally said is that the clients can still somehow malleably generate ciphertext that do not actually encrypt anything. And that is still a problem here for us, for Willow. So we call this the correlated ciphertext attack. And the idea here is basically, like we could have the server and one of the clients collude to choose their ciphertext in a particular way that they sum up all the ciphertext of all the other clients except for one target client that they want to uncover, right? And now if you take the sum of these and the sum of this client, which now is a valid sum of all the clients together, and you ask it for decryption, it will just decrypt the secret key for this particular client, right? So yes.
Just a question about ideal functionality. So I guess we've heard about a couple of these different systems today, and I'm wondering, do you have a sense of how much overlap there is between the different ideal functionalities in these things? Are we all solving really the same problem, or are we all solving very different problems, or like somewhat different problems? Like, how do you see it, I guess, with respect to the...
So I think if you really want to specify the full ideal functionality of every single protocol, they would look very different. I think already in the Willow paper, we have at least 2 different ideal functionalities depending on the particular protocol that you're looking at. So there are different variants of the protocol that solve different things. I think you can probably write down one that covers all of the works that I've mentioned so far in some way. But yeah, I agree. For example, the PKI plus non-PKI versions of protocols, that has to be accounted for in the ideal functionality, right? So you have to somehow work in the PKI hybrid model, or you don't. And
yeah, I guess I was wondering, like your statement that this is already present in the ideal functionality makes me wonder, well,
which ideal functionality is that? Yeah. Maybe I should have had a slide here to actually show the ideal functionality. What I'm thinking of is this, you have a black box, everybody submits the inputs to the black box sums them up and gives you the sum.
I guess the everybody is the question.
Yes. Now, if the black box checks your ID first, that's very different from, you just submit a ballot. Yeah. But yeah, so I was thinking of one where there's no PKI, and of course, if you to the black box add the PKI, so we add some kind of authentication step where only authenticated clients can submit something, then the possible implementations change a lot. Yeah. So in Willow, we very much on purpose made the choice to not have any PKI for clients. The reason being that we wanted to support web clients, we wanted to support unreliable, Android devices and so on. That is something that in many deployment settings, maybe you don't have that problem, right? If we think about messengers, everybody has an ID on a messenger. So there, it's maybe not as necessary to avoid this assumption, or yeah. Any other questions?
So I just want to understand, now you're talking about Sibylla attacks, for example, let's say all the clients will be fake.
Yeah.
And they will just target the one on the start.
That is what this slide is talking about, yes.
That's what
Yeah.
you're
So so a PKI would avoid Sybil attacks. So would differential privacy, right? What we have here is even in the absence of Sybil attacks, right? Here we have a single client that is malicious. All the other clients are honest, and we still have an attack. But that is against the implementation of Willow.
a single client is malicious.
Yeah, here we only have this one red client plus the server being malicious. And the only thing that this client does, it chooses its contribution in a particular way. So it chooses its contribution to be the sum of all the clients except the one we are attacking.
So he should have access to all the ciphertext.
Yeah, because it's colluding with the server, so it can just read the submissions of the other clients. I'm going to show how we solve this. So that's the reason we need zero knowledge proofs in Willow. And I think that also, So the adversary, one observation here is the adversary doesn't know what it's encrypting here, right? So since it's not actually encrypting something, it's just summing up other things, it doesn't know what's the plaintext corresponding to that. So if we just ask every client to provide a proof that they know what they're encrypting, a proof of plaintext knowledge, then this problem goes away. And we can prove that this is enough to actually give us security. So we need zero knowledge proof of plaintext knowledge for this additively homomorphic encryption scheme. So now if we think of the ciphertext, we shorten it here as CI of client I, then basically we want a proof that a particular commitment to a ciphertext is a correct commitment computed on a correctly encrypted version of the secret key that this client knows. And this commitment can be a short, additively homomorphic commitment. So it, in particular, what this will buy us is that the decryptor committee, it has to verify these proofs, of course, but it doesn't actually need to download all the individual client ciphertexts, the witnesses, to check the proofs. It just needs to have the commitments. And it checks that the sum of commitments, in fact, sum up to a commitment of the thing it's asked to be decrypted, and that the proofs of all the clients that they verify. Now, what's an issue with that approach? Remember that we want lightweight committees, right? So the total work here is linear in the number of clients. It's not linear in the total data that the clients send up, so it's still smaller than the ciphertext, but still it's linear in the number of clients. So ideally we have to get that down somehow and make sure that committee members don't do too much work. What we did in the original Willow paper was to distribute the work across many, many committee members. So intuitively, if you think, okay, you have total work O of n, you can split that up across square root n members of the committee, and each of them only does square root n work, right? So that's the intuition. In practice, it's not exactly as easy, but that's about what we achieve with Willow. So the idea is that we distribute this verification of the knowledge proofs in a Merkle tree kind of structure. So we have this aggregation tree that we call it, that has sorted commitments sorted proofs and commitments on the input here, right? So this is all in order of some client ID. And this allows us to make sure that, okay, if there are duplicates in this tree somewhere, right? So if the server somehow tries to cheat and include clients multiple times or anything like that, then we will catch the server because we will see the two of them right next to each other. Now, because of this property, now we can give each of these partitions, we can give to a different committee member. So that way, not one client has to see all of the client's proofs, but they can be verified in a distributed fashion. So yeah, now every committee member just has to check that the partition that they get, the leaves are in sorted order, and then it has to somehow check that this aggregates correctly up to the root, so that the sum of commitments at the inner node is in fact the sum of the commitments that it got from the server and so on. So maybe to go into a little bit more detail, on a leaf node we have a proof, or we have a proof and a commitment on every leaf node. And then on the inner node, we check the proof, and then we sum up this commitment on the inner node, and then we just check it, we hash it, and we check it against the Merkle path that we got from the server, whether that is in fact the right partition that we should have gotten. And we can do that like on the inner nodes as well. We just sum them up, we check the hashes against the Merkle path and so on, and at the end we just have a root hash that we have to agree on in the committee. And if that is the same across all the members, then we can be sure that every client was verified correctly, was included at most once, and that the sum we're decrypting in the end is in fact the sum of these clients' contributions. Questions? Yeah.
So how do you choose the committees?
How do we choose the committees in Willow? We assume they're there.
I guess.
So we don't have a protocol to select them.
Yeah, I guess I was just thinking back to the PKI question again. It's like if you're picking, 10 members out of a set. Yeah. I'm like, which the set? I guess is the set. How do you specify the set out of which you're picking the users? Even?
Yeah, I think that's a very, very good question that a lot of the works on committee-based aggregation have. I'm not sure if Flamingo, for example, had a solution, or I think a lot of the works, they just assume the committee is there. And how to select it, again, there are very many different threat models that you can have in order to actually do the selection. I'm not aware of any pure crypto protocol in the single server model that doesn't assume, an external source of randomness or some kind of, immutable ledger or anything like that that solves that problem. So I think there are different kinds of assumptions you can make to solve that problem, but yeah. Yes, you can in particular think of a static committee here, or you can think of a randomly sampled one at setup time, and at setup time maybe we're semi-honest and that way we can sample it randomly. But Tim, go ahead. Or maybe Hilda, you go first. I don't know.
Thank you. Can you speak to the relative sizes of the population of clients contributing versus the size of the committee?
Sorry, can you say that again?
What's the proportion of the size of the committee versus the number of clients contributing?
So, as I said here, right, we have total work is linear of the committee. We can choose the size of the committee roughly, but if we want each committee to do sublinear work, then we have to at least to have something like square root n number of committee members, so square root number of clients, which is an issue in Willow. Like that makes the committees pretty large. Yeah.
Thank you. Yeah. So what happens if verification fails? So maybe is that covered in the threat model? Like how do we know? Is there a way to figure out if it was a client or if it was the server?
Yeah. So in practice, the server, before it constructs this aggregation tree and hands it out to the committee, of course it should verify it itself. Otherwise, you know the protocol is going to fail, and the server is the one who wants the result at the end, right? Like in practice, when there's a client that submits a failing proof or something, you just exclude the client, right? Yeah. The same thing as if the client had dropped out. Okay, but actually, Tim, your question was perfect. So one of the big issues of Willow is that it has these huge committees, right? In order to have the committee member work sublinear in the number of clients, we do need a lot of committee members. So how can we improve that, right? Like what's stopping us from somehow making the committee work constant or at least sublinear without having a lot of committee members? And that's what we solve in this follow-up work, WillowFold. So the idea here is that the server doesn't delegate the verification to the clients, but it does the verification locally, and then it just proves to the client that it did the verification correctly. Right? So we have this entire aggregation tree, and basically we want to give to the clients a very short proof that we built this tree correctly and that it all checks out. So, of course, what does that formally mean? So this brings us into this space of recursive zero-knowledge proofs, or as they're also called, proof-carrying data. The idea here is that at every inner node of the tree, we now also have a proof. So we don't only verify proofs at the leaves and then just sum up the commitments and have consistency that way, but we also have a proof in the middle layers that verify the proofs of the child nodes. And then in the end, we just send a single root proof to all the committee members. They have to agree on the hash of that and then just verify that. So, sorry, there's a question in the back. Yeah.
So in your model, you have all of your leaf nodes at the bottom, and then your committee members going up. If I am understanding correctly, the committee members are also contributing data. Are they included in those leaf nodes, or at every step going up, do they also contribute data?
Yeah, so the committee members could be the same, could be drawn from the same population that also contributes the data. That is not a requirement. It's two different roles that could be done by the same party.
Okay.
The data is contributed in the beginning. So at the beginning, the server gets all the contributions from the clients, all the data, whether they're committee members also or not, doesn't matter. Then it builds a tree, and then it gets sent for verification. So at that point, there's no additional data coming in.
Sorry, I also have a question. I'm still confused about your attack setting.
Yeah.
How do you still solve this problem without signatures? Because the server doesn't need to collude with any client. If the server knows that there's one honest client, it can generate fake messages for all of the rest of the clients, right? And then ask the committee to verify. So how do you solve this without signatures? I'm a bit confused.
So you're not talking not about this attack, but about this Sybil attack setting.
So why what I'm saying doesn't fall in the next attack that you showed? Because again, I'm trying to extract the input of one honest party, right? So I'm the server. I'm keeping only the message from this one honest server, and I create fake messages for the rest of the parties, right?
Yeah.
So doesn't it all?
And
fall
that
in
means you know all of the inputs except for one, right? So you basically corrupt all the clients
I
except.
fake them, right? I just because there are no signatures, so nobody can check that.
I think in the threat model, corrupting a client or faking a client is kind of the same thing, since we don't have identities for clients.
So yeah, then how do you solve this one without PKI?
So our solution is we have to add differential privacy. And what I'm saying is that already applies to the ideal functionality. If I have a black box and everybody submits a ballot, if every other ballot is fake and I'm the only real ballot in there, of course, in the end, the black box can do whatever. I will, whoever counts the votes will in the end see what I voted for, right? So we have to have some noise in that functionality in order to get privacy.
Okay, so and in the next attack that you have, you don't, so this one here, right?
So here we only have one malicious client. Every other client, we don't know what their value is.
Okay, and here how do you manage to go by this attack? without the signature?
So this attack relies on the fact that the server and the client collude to craft this ciphertext homomorphically, right?
So you're trying to catch the collusion between the two with the ZK? Because I didn't understand that part. How do you resolve this?
Basically, I'm trying to make sure that this client, anything it can do wrong, will not de-anonymize or will not break the privacy of any other client. So what the client needs to do in order to run this attack is to homomorphically add up ciphertexts from other clients. If I ask the client now for a proof that what it submits is in fact a valid encryption, it cannot do that anymore because it doesn't know what this homomorphic addition of ciphertext is encrypting.
Okay, you want to say something?
Yeah, maybe the point is that in this attack, the malicious client is doing more than just choosing its inputs and excluding some clients. It's actually it's constructing its ciphertext in a way that deviates from the protocol.
Yeah, exactly.
And so I guess, yeah.
Do you need some form of like simulation? Do you need some form of simulation extractability from the proof?
Yes, that is a very good observation, which we overlooked in the original Willow proof. So the original Willow proof, we just say, yeah, it's going to be fine if we have this zero knowledge proof. And in fact, you do need simulation extractability. The Willow protocol is still fine because we use bullet proofs that happen to be simulation extractable. In WillowFold, we fixed that. So there actually we do, I put it on the last bullet point here, we do need simulation extractability, and we do need simulation extractability of this new PCD construction that implements this recursive tree. So that's one of the contributions of this paper is exactly that. The other one is that we need a zero knowledge PCD, right? So the recursive zero knowledge proofs, on the leaf nodes at least, they need to be zero knowledge because the leaf nodes need to hide the client's secret key. On the intermediate nodes, we don't care about that anymore, but on leaf nodes, they need to be zero knowledge. So that's actually like the technical contributions of the WillowFold is that we have a PCD scheme that has exactly these two properties, zero knowledge plus simulation extractability.
I think we should hold the questions because we only have a few more minutes.
Yes, okay, I'm almost done also, so it's perfect. Yeah, aside from technical contributions, we also, of course, solve the thing that we set out to solve, which is to reduce the committee member work by a lot. As I said, in Willow, we have roughly square root n committee members, each doing roughly square root n work, which is a lot. In WillowFold, we can have a committee of constant size. Basically, all we have to ensure is that not a majority of them drop out. So we need to have an honest majority after dropouts. And each of them only does log n work. And so in practice, what that means, if we want to sum up over 1 million clients, before every committee member has to do like 500 seconds of work. Now it's 1 second because it's just essentially constant. The caveat is that the server computation goes up by a lot because just the PCDs that we have, they are slow to verify and slow to aggregate. So I think as research improves, this will also improve. And of course, it's like very well parallelizable. So this is more monetary cost than the actual time you need to spend. Input? Oh, no more questions. Sorry.
Just so that we don't have to.
Sounds good. Yeah. Let me come to an end. Then, yeah, another thing that WillowFold has that Willow didn't have is streaming aggregation. So we can aggregate ciphertexts on the fly as they come. We don't have to wait for all of them to be around. So the state, the memory footprint that we have on the server side is a small ID per client. It's not all of the client's contributions. Okay, that was it. Now, if there's time for questions, I will take more. Otherwise, take them in the break.
Time for questions? A couple more?
I guess just really quickly on the previous slide, what was what are you actually aggregating here over 1 million clients?
I'm actually not sure what the ciphertext size is. The important point is that the committee member size doesn't matter for that. And for the server time, it's like super small compared to the proof verification. So probably the time for any vector you aggregate would be the same.
One more question. I guess for differential privacy to protect you against Sybil attacks, you also need to make sure that the server can't send the same data multiple times to be decrypted. Yes. So I guess that seems like something that would require the...
So that's what I meant here by the sorted input commitments. So if the server wants to build a tree that contains your input multiple times, this will be caught at the leaves here because you have to have the same client multiple times there. and you will notice the same client ID. So what we do in the zero-knowledge proof, we basically have a randomly selected client ID that the proof is tied to via fiat Shamir. So if you have the same ID twice, you will see that.
But I guess I could do one aggregation and then another aggregation, and I submit the same report again.
I mean, in practice, you would probably have an aggregation ID, and then you tie your proof also to the aggregation ID. But yeah, that's a valid concern.
I have one more question while Tim sets up, maybe. So, wasn't quick enough to catch why you needed simulation extractability? What goes wrong if you don't have it? Is it easy to see or not so easy to see?
I mean, just that you can't prove simulation security of your protocol VM. So in the proof, there's one step where you need to be able to extract what the kind of.
Anyone else? Great. Let's thank Philip again.